My name is Nigel. Hi, I'm going to talk about numbers. What are they? Where do they come from? The starting point that I'm going to is 1. I think we're all familiar with the number 1. Uno, eins, whatever it is in your language, or just a plain vertical line, or the number 1 written like that. I could have started earlier, but it's not necessary, and I would have spent a lot of time getting to number 1. I think everybody's used to the idea of a 1. We're not really unhappy with 1. The problem that most students have is when they get to numbers like the square root of -1, complex numbers, as they're called, or imaginary numbers. They don't feel that that kind of number is on the same sort of footing as, say, the number 1. But that's not true. All numbers have an equal validity. So in order to start this process, we have to do something with the number 1. We have to do some sort of what in mathematics is called an operation. Think of it as a sentence that we have nouns and verbs in a sentence, and okay, there are other parts of speech, but the nouns are the objects, the things we're referring to. The verbs are the doing words. These are the actions. And in maths, the numbers are our objects, and what they call operators are the actions. So for example, we can form a sentence called an expression in maths, and there's an example, 1 + 1. I think we're all fairly happy with that. Although if you're a computer scientist, you would realize that there's 2 ways of doing this. There's adding 1 to 1, that's one thing, and then adding 1 to 1 and evaluating what you get, the number that you get, is slightly different. And in mathematics, if you want to show the difference between those 2 things, what you can do is you put a bracket around the 1 + 1. The 1 + 1 with a bracket around is explicitly saying this is a number, this is what you get when you evaluate what's inside the bracket, which in this case is 1 + 1. So my first question to you is, what number do you get when you add 1 to 1? And the number that you get is what is put on the right-hand side of this equation that I've drawn. I've also put the equation sign is the equal sign. What this means is that you evaluate the thing on the left, and then the thing on the right is what you get when you've evaluated it. So what's the answer? Anybody take a guess? You're all wrong. The answer is not 2. The reason why the answer is not 2 is simply because I haven't actually mentioned 2. I only mentioned 1. That was my only number. So if 1 is your only number and you're adding 1 to 1 to get another number, all you can do is say that 1 + 1 with the brackets around it is equal to this thing, which is 1 + 1 evaluated. When you've done that, then, and only then, can you say, well, all right, I'm going to now define something, define a new number, and it's what you get when you add 1 to 1, and I'm defining it. That's why I've used 3 parallel lines rather than 2. And I'm putting there this rather funny shape, looks like a swan, which we recognize as the number 2. I don't have to use that particular shape. I could use any shape I like. I can put a smiley face in if I want and call that the number 2. So the number 2 that we use and we're all familiar with, is just simply a definition of what you get when you add 1 to 1. And if you carry on adding 1 to 1 and add other numbers in as well, you end up with what they call the natural numbers. These are all the numbers from 1 all the way up to infinity. And in mathematics, they're called natural numbers, and they are represented by this rather funny capital N. It's what they call a double strike, and that represents the natural numbers n, 1 to n, 1 to infinity. Now, there's a rule in math. It's not exactly a theorem, and I'm sure there are things that go against it, but there's basically not much point to doing anything in maths unless what you do can be undone. In mathematics, this is called an operator and an inverse operator. So if we have 1 plus 2 equals 3, and we've introduced this symbol for 3, then we can turn this around and say, well, 1 is equal to the 3, which is the answer, minus 2, and the minus is our inverse operator for addition, otherwise known as subtraction. Now, there's no problem with this, except what happens if you want 3 minus 3 or 3 minus 4? In other words, if the two numbers are the same with a minus sign, or you get the first number is smaller than the second number, then you can't use the natural numbers as defined. So we have to introduce new numbers. And clearly for 3 minus 3, we have to introduce the 0. There's the 0. And for the case where the second number is bigger than the first, we can introduce a clever trick of just putting a minus sign in front of all the natural numbers. So what we end up with is a complete set of numbers from minus infinity through 0 all the way to plus infinity. And this set of numbers is referred to as the Z numbers. Z stands for the German word for number, which is Zahl or Zahlen in their plural. A lot of this work was done by German mathematicians. Well, we can continue this game of introducing operations and their inverses, and where we need to, we can define new kinds of numbers. So we go to multiplication, for example, and that's the x sign or the times sign. There's no problem with that. If you start with any z number and you multiply it with any other z number, then the answer will be another z number. On the other hand, the inverse of multiplication is division. Here we have a problem. Supposing you have 2 divided by 3. That's not a z number. It's not a natural number. It's not a negative of natural number. It's not a 0. It's not on our list of z. So we introduce a new number, which we call q, the quotient numbers. So 2 divided by 3, for example, is a quotient number. But that just extends our numbers from natural numbers to z numbers to quotients. We can also look at squares, square of a number, again, no problem. If you take the square of a z number or even a quotient number, if you square it, you'll end up with a quotient number. But if we take the square root, which is the inverse of the square, we find there's 2 problems. The first problem is if we take something like the square root of 2. Square root of 2 is not a quotient number. you can't write the square root of 2 as the ratio of two z numbers. And we refer to the square root of 2 and other numbers like it as the reals. And we use the double symbol R there, the rather funny capital letter that's double struck R. That represents the real numbers. The real numbers are all the numbers that you get on a line. So if you have a line from 0 to 1, for example, then any point on that line will be on the reals. It may be on at each end, it may be on the z's, and there may be numbers in there which are on the q, but all the numbers there will be on the r, and the square root of 2 is one of them. The other problem with square roots, of course, is if the number that we're square rooting is negative. And again, we have to introduce another number. This time we introduce the complex numbers. The complex numbers are represented by this funny C symbol. So that leaves us with NZQRC. The natural numbers, the Z numbers, the Q numbers, the reals, and the complex. And I've shown them on this diagram, which shows how they're nested together. So the complex numbers include all the others. The R numbers include the Q, Z, and N, and all the way down to the Z numbers include the N's as well. The N's, of course, are on their own. And NZQRC is basically the different kinds of numbers that we come across. And because we introduce each of these numbers from their operators and the inverse operators, they're all on the same sort of par, and they're all valid. Valid is a good word. It's better to use the word valid than the word real, because we use real for the R's. And the C's, we use the word complex or imaginary for parts of them. They're not, complex numbers are no more imaginary than any other number in the usual way of using the word imaginary. But in the mathematical way of using the word imaginary and real, that's different. So I hope that's sort of explained to you a little bit where numbers come from and how valid they all are. This is a good place to stop, and I'll leave you with a little advert for our website where we produce math and physics textbooks. Goodbye.